Hi everyone, in this video we're going to go through the answers to the practice exam 3. This covers this most recent unit up through substitution elimination of alcohols and alkyl halides and synthesis. Okay, so of course nomenclature makes an appearance. The only new thing we added this time was the nomenclature of alcohols. So alcohols get priority in the name over other functionality. So 1, 2, 3, 5, 6, 7. I gave the alcohol number 1, and then I numbered to give the alkene second priority in the name for the lowest number. So we have a cycloheptanol. All right, since in a ring the lowest number is 1, I can leave out the 1 here. If you have it, it's fine. Actually, it's a cycloheptenol, so it would be cyclohept-2-enol. And then we have a substituent at carbon 5, a 5-tert-butyl. And so we put this together, 5-tert-butyl cyclohept-2-enol. Okay, we have to indicate stereochemistry. So looking at my 2 chiral centers at carbons 1 and 5, alcohol is number 1, 2, 3. This is a clockwise rotation. This would be R. And then 5, we have carbon, carbon, carbon. So what's attached? Here we have C, C, C. Here we have C, H, H. And here we have C, H, H. So the tertiary butyl gets priority number 1. Then we go on from the CHH pieces, and we have what's attached here is CHH, and what's attached here, we count the double bond twice, is CCH. This is 2, 3. This is a counterclockwise rotation. This is S. So we have a 1R5S out in front. Moving on. Hopefully having one naming example will save some time in the long run. Then we're into reactivity and mechanisms. So, this unit was exclusively substitution elimination. So there's a lot of different things we can talk about here. I can't test you on everything, so there'll be a smattering of what I can squeeze into the exam. So I'm looking at these. Circle the most reactive substrate from the reaction series below. Explain briefly and write the product that you selected. So I have a secondary alkyl halide for all of these, and then I have a weakly basic nucleophile, and so it's identical for all of them as well. So I have the same substitution, same nucleophile. The only difference here is leaving group. So this must boil down to leaving group ability, and the best leaving groups are the weakest bases. And looking at Br versus I versus F versus Cl, and their basic form as the anions, I- is the weakest base. So this would be the fastest reaction. Of course, secondary with a weak base goes by SN2. This would be inversion of configuration. I- is the weakest base, therefore it's the best leaving group. Right. Consider the pair of reactions below. We have a secondary with a strong base, secondary with a strong base. Right, so which reaction A or B would proceed at the faster rate? Okay. Well, same base, secondary, then we must consider, what is this going to be in terms of the outcome so we can think about this correctly. Of course, it would be E2, and that's part B. Perhaps I should move that up here. Oops. Anyway, then circle the letter that's faster. Okay, so I gotta figure out what's faster based on the chairs here. So I'm gonna draw my reactive chair and see where my beta hydrogens are. Okay, and then for B, the same idea. I'm drawing the reactive chair, so my leaving group has to be axial. And then we have to make sure that we have the same relationship here, cis for both of these. So we have the cis 1, 2, this is up, and the Br is up, and the isopropyl is up, right? So the reactive chair here has 2 axial, so this is the less stable, and therefore would be at a lower concentration at equilibrium. This one where we have 1 axial, 1 equatorial, the large group is equatorial, so this is the most stable chair. Therefore, it is the highest concentration at equilibrium. Therefore, option A would react faster because the reactive chair is the most stable chair and therefore present at the highest concentration. And we know the rate is proportional to some constant times the alkyl halide concentration times the base concentration in an E2 reaction. Okay. Question 3. When the following compound undergoes solvolysis in ethanol, 3 products are obtained. Okay, I have an alkene. That looks like substitution. That looks like substitution. What mechanisms is or are occurring to produce these products? Well, if we are producing A here, this has an alkene. This has to be an elimination. We look at this as primary allylic under very weak basic conditions. So this would be SN1E1. So this would have to be E1, and this is SN1, SN1. And another clue that I see that it has to be SN1 is the presence of compound B, because this is not a direct substitution of the leaving group. The only way for this to occur would be through a resonance contributor of a carbocation. So SN1, E1 are competing here. After you separate your products and collect IR spectra, what signals would you look for to differentiate between product A and B, C? Okay, so A would have the alkene stretching around 3,100 reciprocal centimeters, and then B would have characteristic peak. So this would be only kind of the diagnostic peak that you'd look for, and then B would also have that around 3,100 plus a CO single bond stretch around 1,100 reciprocal centimeters. Okay, so you'll have the chart provided to you, and you can use that to predict how you might differentiate those products. And then we're showing curved arrow mechanism for the observation of product B. So I'm going to just redraw this, what I'm starting with and where I'm going, so that I have that right in front of me. Okay, so all right, so loss of leaving group is the first step of an SN1 reaction. I generate this allylic carbocation. There is resonance. Be careful of your arrows. I will deduct a point for inappropriate arrow usage. And then ethanol would intercept this contributor, leading to the oxonium intermediate, and then there's another proton transfer to arrive at the product. And this, of course, is driven toward this neutral product because of the high concentration of ethanol as the solvent. There is plenty of it around. And this is, of course, completely reversible. And so we use Le Chatelier's principle here to drive this. All right, now, question 4. Consider the elimination reaction shown below. So elimination, this is a strong base, so it'd be E2. Draw the complete curved arrow mechanism for the conversion. E2 is quite easy. It's one step removal of the beta hydrogen brought by the base. Loss of leaving group is concerted to give you the E alkene predominantly, and that's what's shown up above. Of course, either E or Z could form here because I have 2 beta hydrogens that could lead to either of those products. All right, complete the reaction coordinate diagram for the reaction, label intermediates, transitions as So this is a one-step reaction. This would be a transition state. Draw a reactant and product in the scheme below that would have a faster reaction rate. So I have a secondary alkyl halide up here. We know that the reactivity for E2 reactions favors tertiary alkyl halides. So something tertiary, there's a wide range of options here that would be faster. Okay, so it must be tertiary, faster under E2. And then part D, add a second curve to the coordinate diagram for the reaction in part C. So if it's faster, it must have a lower activation energy and would mirror that, but at lower energy. Okay. Question 5. Complete the reaction schemes below with a reactant or major organic product. Okay, and use stereochemistry as needed. Okay, so I have a secondary alcohol with a strong acid. The conjugate base is NO3 minus. This is a poor nucleophile, so this must be E1. Strong acid favors cationic intermediates. Poor nucleophile must be elimination. So I'm going to get major product here as the trans double bond, and the minor product as the cis double bond, and I suppose I should have 3 boxes because this would also be a minor product. Okay, this is why it's a practice exam. Then in the second one, I have a strong base, secondary alkyl halide. It's pretty sterically hindered with all of this, so substitution is certainly not going to be favored. We have the strong base, so E2 will be predominant here. We want to consider the Newman projection because I only have 1 beta hydrogen. You may be catching on here that, okay, it's on a wedge and so is the chlorine, so these are syn as drawn, and so I would need to rotate about this central bond, and right away you may be able to come up with the fact that this will end up being, being cis rather than trans. If you want to draw the Newman projection, you certainly can. So I'll look up this way. Hopefully I can draw it right the first time. H methyl, no, I'm already messing it up. The front carbon has chlorine on it, so I have chlorine, hydrogen, and then up top I have this R group, I'll call it, and then I have in the back H methyl and then ethyl back here. Okay, I'll rotate my back carbon around such that H is here. CH3 would be here. So that means my R group and my ethyl will be on the same side in my product. My R group and my ethyl will be on the same side of my product. So I got that taken care of appropriately. I also forgot a methyl group here because on this back carbon I have a methyl group, and it is on the same side as the H here, which you don't need to draw, but you could. Okay, part C. I have an alcohol, it's primary, NaOH. So this must have been through an SN2 reaction. This could be any alkyl halide, a bromine, chlorine, iodine, not fluorine. Tosylate doesn't make sense necessarily because you make a tosylate from an alcohol and then you're making an alcohol here, although I probably wouldn't dock you for that, but just keep in mind it doesn't make sense. Here we have strong acid. The conjugate base is Br minus, good nucleophile. So this will be SN1. Again, strong acid, cationic intermediates. So we have loss of leaving group to give you the carbocation. We have branching next door with a ring. So a ring expansion, the major product would be this, and then the minor product would be the racemic mixture of alkyl bromides. Let's make that fiber ring better. Okay. That's all she wrote on that one. And then here we have to figure out what the reagents are. So I'm going from a primary alcohol to an alkene. And the reagents to do that, I need to do an elimination. When you eliminate a primary leaving group, you need a bulky base. So potassium tertiary butoxide and tertiary butanol will work. But OH is a poor leaving group here, so we've got to make that a good leaving group. So this will end up being 2 steps. You can choose tosyl chloride and pyridine. You could also use thionyl chloride to make it an alkyl chloride first, or PBr3 to make an alkyl bromide. So there's a number of different options here, but that's the gist. You have to make it a good leaving group, and then you eliminate it with a bulky base. Okay. Now we're getting into synthesis. Ethers can be paired by several routes, one being the Williamson ether synthesis, where an alkyl halide is combined with an alkoxide. Show the 2 possible ways to pair the ethers shown. Only one is a productive reaction. Explain. So we can cleave these ether bonds and get the alkoxides and the halides. The other option over here would be to have the phenolate and the alkyl bromide here. All right, so one of these is productive, one isn't. So you have to think about what kind of reaction this is. It's an SN2 reaction, so we have to consider sterics. Leaving group is the same basicity, nucleophilicity, etc. So we consider the fact over here, we have a primary alkyl halide with a weak base, right? Phenol has a pKa of around 10. And so that would definitely be SN2 for sure. And here we have an aryl halide. Okay, so that's an sp2 center. And right away there, you should see no SN2 on sp2 because the orbitals will not be accessible. That antibonding orbital, right, is in the ring, so it's not available. And then the HOMO is a pi star orbital. So if some nucleophile were going to react with this, it would react with the pi star orbital, or excuse me, the LUMO of the electrophile. So MO theory or just, I mean, both of these explanations are related to MO theory, but the idea is that you can't substitute an sp2 hybridized atom because the orbitals are not accessible, and you know, these HOMO-LUMO interactions are not going to be favored between the carbon leaving group bond. The LUMO is a pi star orbital rather than a sigma star orbital. Okay. Now, a younger Dr. Hauck was in the lab preparing a batch of hexine as a precursor to one of his synthetic targets, and he reacted a vicinal dibromide, shown here with sodium amide, but to his surprise, his yield was abysmal, and despite impeccable lab technique. Can you explain why and what could be done to improve the yield? So it looks like, you know, we know this plus this gives the alkyne. Treated with water to reprotonate at the end of this, but only used 2 equivalents of the base. So what happens is you use 1 equivalent to eliminate once, then you use another one to eliminate again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then an unstoppable acid-base reaction happens to give the alkynide ion, and then with the water workup, you would reprotonate. So this step, the third step, is unstoppable. And therefore, you use NaNH2 3 times, and so you'd need a minimum of 3 equivalents. Otherwise, you run out of NaNH2 before you've consumed your reactant. And so he would need to add 3 equivalents for a better yield. And then in these last examples of synthesis, you only need to choose 2. So choose 2 that you want to be graded and mark an X through the letter you do not want to be graded. I will work the answer for all of these. All right. So all you're doing here is identifying reagents you would use, draw the sequence of reactions, and show all intermediates but no curved arrows. Okay. So intermediates are, you do a reaction, you make a product. That's an intermediate. You do a reaction on that to make a new product until you get to the final stopping point. All right, so working backwards and asking yourself these questions are going to be keys to being successful at synthesis. So first question is, am I making new carbon-carbon bonds? So I have a 6-membered ring with 2 carbons, 6-membered ring with 2 carbons. The answer to that is no. So I do not need to do any alkylations here. What's changing? I have an alkene going to a dibromide, and this is a geminal dibromide where those bromines are on the same carbon. And so you want to think, okay, well, how can I make that? Well, I can make that one way from an alkyne with HBr, 2 equivalents. And then how do I make alkynes? Well, where am I starting? I'm starting with alkenes. Okay, well, alkene to alkyne, I know that is a 2-step process. This is terminal, so I need 3 equivalents of that, followed by some acid, and water is a strong enough acid. Think about the pKa difference there. And we have a vicinal dibromide here, which we can make with Br2 and some non-polar solvent like chloroform or methylene chloride. Those would be interchangeable there. Okay. Are there variations on this? Not really. You can't really do part A any differently than that. Okay. And oftentimes there will be multiple answers here. So keep that in mind as you're solving these. All right, this is an azide. Am I making new carbon bonds? 1, 2, 3, 4, 1, 2, 3, 4. So no alkylations here. Azides can be made through SN2 reactions with sodium azide as the nucleophile, and let's say DMSO, it's a primary. So I need a primary leaving group. Let's use Br. And then to make that primary bromide, can't make a primary bromide from an alkene, but I can make a primary bromide from an alcohol, PBr3, pyridine. Alternatively, you could use a tosylate to get a good leaving group. And then do the same reaction. You could use dinochloride here, again, interchangeable stuff. So how are we going to make that alcohol? Okay, well, I can make primary alcohols from hydroboration oxidation. This is longer than I intended it, by the way, but BH3THF, NaOH, H2O2, and water. And to move the double bond, which we did this in class, so it's not that unusual, we would use something like HBr followed by an elimination reaction. You need a sterically hindered nucleophile to make the Hoffman product. So we have, 4 or 5 steps, depending on